Hey guys, welcome to the Level 2 Chemistry 2020 Structure and Bonding paper. Let's get started. So question 1, complete the table for the given substances in their solid state. So for silicon dioxide, this is a covalent network. So covalent network, and a covalent network just has non-metal atoms in it, and the attractive forces are going to be covalent bonds. For chlorine, it's a molecular, because if we put like a staircase between the boron, okay. So if we put a staircase between the boron and aluminium, like this, then everything to the left is going to be metals, except for everything on the left are metals, except for hydrogen obviously, and then everything on the right, they're going to be non-metals. So chlorine we can see is on the right, so it's a non-metal. So it's going to be a molecular solid. So coming back to this table here, chlorine, it's a molecular solid. The type of particles, it's just molecules. And the attractive forces, they're going to be weak intermolecular forces. And potassium chloride, we have the air staircase has disappeared, but I'll draw it again. So potassium, okay, this is a metal because it's on the left, and then again chloride, that's a metal and a non-metal, so it's an ionic solid. And the type of particle, they're just ions, so the positive K plus ions and the Cl minus ions. And then the attractive forces are the electrostatic forces between these opposite charges, because there's that electrostatic attraction, so we can just write ionic bond or electrostatic attraction, whatever you want to write. So the electrical conductivity of silicon dioxide and potassium chloride in different states is given below. So silicon dioxide doesn't conduct electricity when it's solid or molten, whereas potassium chloride, it conducts when it's molten. So for there to be electrical conductivity, there needs to be free moving charged particles. That could be a delocalized electron. So for silicon dioxide, it has this red here as the silicon atoms, and then the blue ones are oxygen, as it says here. Each silicon over here is bonded to 4 oxygens, and there's no delocalized electrons. No delocalized electrons in both its solid state, when it's solid and when it's molten. Solid and molten state. So when it's solid or molten, it doesn't have delocalized electrons or free moving charged particles, so it won't conduct. So therefore it won't conduct. Now looking at our ionic substance, this is in our case going to be a K plus, not the Na, and then Cl minus. So the ion our KCl is held in this kind of 3D lattice ionic. It's these positive and negative ions ionically bonded, so these are the ionic bonds, and they're held together in a 3D lattice shape, and these are fixed in place. These cannot move around, so they're fixed in place. That means there's no free moving charged particles or free moving ions. Therefore, it won't conduct. And we can just write this like this. So for electrical conductivity, requires a substance to have mobile charged particles, so that's like free moving. Silicon dioxide is a covalent network solid made up of silicon and oxygen atoms, so you could just write atoms strongly covalently bonded in a 3D lattice. There are no delocalized electrons and in both its solid and molten state, so it does not conduct. And for potassium chlorine or chloride, how do you say it? Potassium chloride, there's no free moving. So like I said, in the lattice they're fixed, they're rigidly held, but when it goes molten, so this is when it's solid, but when it goes molten, these bonds break. So ionic bonds break when molten, and so ions are free to move. Therefore, it will conduct when it's molten. And that's what we've got over here. So when it's held in the 3D lattice, when it's solid, the ions can't move around, so it won't conduct when it's solid. But when it's molten, the ions are free to move, able to move freely, so it will conduct electricity. Moving on to the next question. Solid potassium chloride is soluble in water. Chlorine gas is not readily soluble. Use a knowledge of structure and bonding. Okay. So they want us to draw a diagram. So if we have water, just do a blue here. Let's say we have let's say we have a beaker here. Actually no, we'll say this whole thing is water. This whole box here is water, and we have our water molecules in here, and this has a bond dipole. Water has its bond dipole, the way the negative is on the with the oxygen and the positives are on the hydrogen ends. And then when you put potassium chloride, the solid, into water, it's going to break apart into its ions. So it's going to go into its K plus and its Cl minus. It's going to break up into those, and the bonds between. So if there's another water molecule, I'll just draw that here. H. So this has its dipole here. So the attractions between, I'll change the color. So the attractions between these, the water molecules, those are the attractions that hold the water molecules together. And then there's attractions between this, but then there'll be new stronger attractions between, I'll just use a different color, yellow. Let's say yellow is a stronger one. there's going to be attractions between this positive here and this negative dipole of the oxygen, and these are stronger than the, so these are stronger than the red. This one here, this is weaker. So this is gonna be attracted to this oxygen, this K plus, to the oxygen side of the water molecule, and this chlorine negative ion is going to be attracted to the positive end of the water molecule, the positive hydrogen ends. And for chlorine gas, it's got, so we've got our, I'll draw it again, our water molecules, H, and they're attracted to each other. H. So there's attraction over here. There's attraction here. And then there's going to be another attraction that is between the chlorines. So that's, this attraction here. In this case, this attraction between the Cl and the oxygen isn't strong enough. So I'll just make it purple. This isn't strong enough. It's insufficient. So these are stronger. So these chlorines just want to stay together. And these water molecules just want to stay together, because the attractions between the chlorine and the water molecules aren't strong enough to overcome those existing bonds. So how we can write this, we can just write that potassium chloride is an ionic solid, and when it dissolves in water it separates into its ions. Like I said, the ions are charged and attracted to the ends of the polar, so they're attracted to those oppositely charged ends. Like I said, the negative charge in the oxygen end is attracted to the positive, and the slightly positive hydrogen end of the water is attracted to the, so the positive is attracted, so the opposite charges are attracted. This causes the ions to be surrounded by water molecules and it dissolves. The solid is soluble because the force of attraction between the ions and water is strong enough to overcome those existing forces holding the ions together along with the forces holding the water molecules together. So, like I said before, it's strong enough to overcome those existing bonds or forces. Chlorine is a non-polar molecular substance made up of those Cl molecules. So they're held together by weak intermolecular forces because it's a molecular substance. So for chlorine and water, the iodine-water attractions are not strong enough. Like I said, the attraction between the H2O and the Cl, they're not strong enough to overcome the attraction over here and the attraction between the water molecules. So that's why chlorine won't dissolve in water or is insoluble. Moving on to the next question. Draw the law structure and name their shapes. So for CS2, the carbon is going to be in the middle because carbon has 4 valence electrons, so it wants four bonds to gain a full outer shell, I guess. Sulfur has 6 valence electrons, so it wants 2 bonds. So yes, they each want 2 bonds, so 2 bonds. This carbon has its 4 bonds, it's happy. This one's 8 electrons around it, so 2, 4, 6, 8. That's happy. This one needs 2, 4, 6, 8. This one's happy, so there's 2 areas of negative charge, so it's going to be linear. NOCl, the nitrogen has 5 valence electrons, so it wants 3 bonds. Oxygen has 6 valence electrons, so it wants 2 bonds. And our chlorine has 7 valence electrons, so it wants 1 bond. So the nitrogen will be the central atom. Oxygen, we can put it here. You can put it however you want, really. So 2, 4, 6, 8, that oxygen is happy. This nitrogen wants 2, 4, 6, 8. That's happy. The chlorine wants 2, 4, 6, 8. That's happy also. So around the nitrogen there's 1, 2, and 3 areas of negative charge. So there's 3 areas of negative charge. This double bond here only counts as 1 area of negative charge, even over here there's not 4. That's only 2 areas of negative charge. Even triple bonds, they count as only 1 area of negative charge. So there's 3. That means it's going to... There's 3, but there's 1 non-bonding region. So it's going to be a bent shape. CH2F2. So carbon is a central atom. It's going to want 4 bonds. So H, H, F, F. The hydrogens are happy. The carbon's happy. These fluorines want 8 electrons around it. So 2, 4, 6, 8. 2, 4, 6, 8. With these lone pairs, now the fluorines are happy too. So there's 4 areas of negative charge, no non-bonding regions, so it's going to be a tetrahedral shape. CH2O and NF3 have the same number of atoms in their formulae, but have different shapes. So this one here, CH2O, it's got 3 around the central atom. So does this, but these actually have different regions of negative charge around it. So this one has 1, 2, 3 regions of negative charge. This one has 1, 2, 3, 4 regions of negative charge. So they're going to repel differently. 4 regions of. So these regions are going to repel for maximum separation. So that's why the angles are going to change. The shapes and angles are going to be different. The bond angles and shapes. So how you can write this? You can write it like this. CH2O has 3 regions of negative charge around the central carbon atom. These repel for maximum separation, like I said, into a trigonal planar shape with bond angles of approximately 120 degrees. So there are 3 bonded regions and no non-bonded regions, making the final shape trigonal planar. And then for NF3, there's 4 regions of negative charge around the central nitrogen atom. They're going to repel for maximum separation into a tetrahedral shape, so it's going to be different this time because there's more areas of negative charge, more repulsion, and it has bond angles of 109.5 degrees. There's 3 bonded regions and 1 non-bonded region, so the final shape isn't going to be tetrahedral, it's going to be trigonal pyramid. Moving on to the next question. A molecular compound consists of 2 different elements, X and Z, and contains 3 atoms. Its formula is ZX2, so the elements have different electronegativities. Depending on the identity of the elements, the molecule could be either polar or non-polar. So if the molecule's polar, so there's 3 atoms, so there's going to be Z, and then 2x atoms. So if it's polar, it's going to be bent, and if it's non-polar, it's going to be linear, and I'll explain that in a minute. So if ZX2 is polar, this is like the 2 down here, is polar, this indicates that the ZX bonds are not spread symmetrically around the central Z atom. So there must be either 3 or 4 regions of negative charge with only 2 bonded atoms, therefore the shape must be bent. So we know it has to be this, Z, X, X, and then, so it has to be like this. There's going to be 2 bonds. If it's going to be polar, then there's going to be either 1 lone pair on it, or there can be 2 lone pairs on it. Either way, the shape is going to be bent, because it's as soon as a central atom has a lone pair, it's not a symmetrical shape. We don't see it like that. This may look geometrically symmetrical, but that's not how we do it. And in chemistry, if there's a lone pair on the central atom, then it's not symmetrical, so it's going to have a molecular dipole, so it's going to be polar. So if ZX2 is non-polar, this means that the polar ZX bonds are spread symmetrically, so that means there's no lone pairs on the central atom, and it's symmetrical. So the molecular dipoles are going to cancel too. So around the central Z atom, there must be only 2 regions of negative charge around this Z atom, both bonded by X atoms in a linear shape. So we know it's got to be this. And for it to be symmetrical, there can't be lone pairs here. We can't put those there. So it has to be like this. So that makes the shape linear. That's the only way to get it non-polar. Moving on to the next question. Sulfur dioxide can be made by burning sulfur in an excess of oxygen. Calculate the mass of sulfur burned when 740. So the mass when 740 kilojoules of energy is released. So we need to find the moles, the number of moles for how many moles releases this much energy. Then we can convert that to mass. So what we can do is, this is 1 here. There's a 1 in front of the sulfur, but you don't need to write it. I'll just write it there to show you anyway. So 1 mole of sulfur, 1 mole of sulfur releases this much energy. When it's negative, when enthalpy change is negative, it's releasing energy. So this is negative 740, but when you write released, you don't have to put that negative sign there. So 1 mole of sulfur releases 296 kilojoules of energy. Now we're figuring out how much moles of sulfur releases 740 kilojoules of energy. So what we can do is we can divide this bottom number 740 by 296. So 740 over 296. That gives us 2.5 moles. Oh no, sorry. Yeah, so that gives us 2.5. Now we can use this number to go back from 296. This here, the energy they gave us for 1 mole. If we multiply 296 by 2.5, we go back to what? The 740. So 740. So this energy times by 2.5 gives us this. So if we multiply this mole by 2.5, we get the moles of how many moles of sulfur releases this much energy. So 1 times 2.5 equals 2.5. So that means 2.5 moles of sulfur releases 740 kilojoules of energy. But that's not it. They want us to calculate the mass. Oh, that just wasn't meant to be covered, but mass is what they want. So what we can do to get mass, got a bit of space. So N equals M over big M. So that's moles equals mass over molar mass. And we rearrange for M because we want to find the mass, the little m. So M equals N times big M. So mass is going to equal, moles is 2.5. I don't want to make it look like divide. 2.5 times our molar mass is of sulfur is 32.1. 2.5 times 32.1. So that gives us 80.25. And we round this to 3 significant figures, 80.3 grams. And that should be our final answer. I should have said this at the start, but I don't have a marking schedule, so I can't confirm if these answers are correct. For question 3a, octane is used as fuel. Classify this reaction as endothermic or exothermic with a reason. So this is exothermic because enthalpy change is negative. Like I said before, if it's negative, then it's exothermic. It releases energy. So it's exothermic. So it releases energy. This is energy. And because don't need to put and because our enthalpy change is negative. Complete including labels the energy diagram. So since it's negative, our reactants are going to be at the top. Actually, make it straight. So our reactants are going to be at the top. Our enthalpy change is going down, and then our products are going to be like under the reactants. So this is our reactants. This is our enthalpy change. That is negative 1018 kilojoules. And then this is our products down here. Next question. Ethanol is liquid at room temperature with a boiling point of 78.4. Explain whether the change of ethanol from liquid to gas is an endothermic or exothermic process by referring to the attractive forces between the particles. Okay. So when any substance goes from liquid to gas, bonds break. So if bonds are breaking, this requires energy in order for bonds to break. So it requires energy. And this energy is absorbed from the surroundings. And when energy is absorbed. So that means it's going to be endothermic, because if for exothermic energy is released, so for endothermic energy is absorbed. Therefore it's going to be an endothermic process. Endothermic process. I think that's all they want. We'll just move on to the next question now. The chlorination of ethene can be shown by the following equation. Calculate the bond enthalpy of the C-Cl bond. Okay, so we're figuring out the bond enthalpy of the C and Cl bond. We're figuring out what it is. Okay, so to get this, we have to use this formula. So change in enthalpy equals the reactants minus products. So this is these reactants here minus these products here. So what we can do is we'll do reactants first. We'll calculate we'll add up all these bond enthalpies. So reactants, we have C2H4, so there's one CC bond, 1 times C, that's the double bond, and that is 614. We have 4 CH bonds, 4 times CH, which is 414, so 4 times 414. And there's only one of this molecule, one of this, so that's good. There's no, sometimes they can put like a 2 here, and lots of people get it wrong then. So 4 times 414 is 1656. What else do we have? We've done this. So Cl, that is 242. So if we add these up, 614 plus 1656 plus 242, we get 2512. That's our reactants. Now we need our products. We have some space. Our products are going to be, we've got C2H4Cl, so this is just this. So we've got 1, 2, 3, 4 CC bonds. Oh, CH bonds, sorry. So we've got 4 times CH, and our CH is 414. 4 times 414, which equals 1656. We've got 1 CC bond, 1 times CC equals the CC bond of 614, 614. What else do we have? We have 2 CL bonds, CCl bonds, sorry, so we have 2 times CL bonds, 2 times CL, but we don't know what it is, so I can just write this as 2x. So what we can do is we add these up. 1656 plus 614, that is 2270 plus 2x. So this is our products here, and this is our reactants. So, and we've got our change in enthalpy, which is negative 148. So using that formula, change in enthalpy equals reactants minus products, we can put it in. So it was a negative 148. Negative 148 equals to our reactants, which is 2512 minus 2270 plus 2x, and this goes out to these numbers here in the brackets. So we get negative 148 equals 2512 minus 2270 minus 2x Now we rearrange, so minus 148 minus 2512 plus 2270 equals negative 2x.